नमस्कार सभी दर्शकों को। मैं आंचलिक विज्ञान केंद्र भोपाल की तरफ से हमारे सभी यूट्यूब के दर्शकों को पहली बात तो नेशनल साइंस डे जो कि हम 28 फरवरी 2021 को मनाने वाले हैं, आंचलिक विज्ञान केंद्र भोपाल, रीजनल साइंस सेंटर भोपाल, एमपी काउंसिल ऑफ साइंस एंड टेक्नोलॉजी भोपाल एवं नेशनल काउंसिल फॉर साइंस एंड टेक्नोलॉजी फॉर साइंस कम्युनिकेशन डिपार्टमेंट ऑफ साइंस एंड टेक्नोलॉजी न्यू दिल्ली के संयुक्त तत्वाधान में 22 फरवरी से लेकर के 28 फरवरी तक नेशनल साइंस डे के लिए ढेर सारी एजुकेशनल एक्टिविटीज़ का आयोजन कर रहा है, जिसमें से आज हम आपके सामने लेकर के प्रस्तुत हैं एक कार्यक्रम जिसके लिए ही हम सेलिब्रेट करते हैं नेशनल साइंस डे, यानी कि डिस्कवरी ऑफ रमन इफेक्ट ऑन 28 फरवरी 1928 को। तो इस एक्सपेरिमेंट को, इस इफेक्ट को सेलिब्रेट करने के लिए भारत हर वर्ष 28 फरवरी को राष्ट्रीय विज्ञान दिवस अर्थात नेशनल साइंस डे के उपलक्ष्य में मनाता है। तो इस विज्ञान पर्व को सेलिब्रेट करने के लिए 22 तारीख से 28 तारीख तक हमने आंचलिक विज्ञान केंद्र भोपाल ने ढेर सारे कंपटीशन जैसे कि ड्राइंग कॉन्टेस्ट फॉर मिडिल स्कूल लेवल स्टूडेंट्स, ऑनलाइन क्विज कॉन्टेस्ट फॉर मिडिल लेवल स्कूल स्टूडेंट्स, आज का कार्यक्रम ऑनलाइन डेमोन्स्ट्रेशन, लाइव डेमोन्स्ट्रेशन ऑन स्कैटरिंग ऑफ लाइट और ढेर सारे लेक्चर्स, वर्कशॉप्स का आयोजन कर रहा है। इस पूरे कार्यक्रम को, इस पूरे पर्व को, इस नेशनल साइंस डे को सेलिब्रेट करने के लिए 22 तारीख से 28 तारीख तक। और ये कार्यक्रम आंचलिक विज्ञान केंद्र भोपाल, नेशनल काउंसिल फॉर साइंस एंड टेक्नोलॉजी कम्युनिकेशन, डिपार्टमेंट ऑफ साइंस एंड टेक्नोलॉजी न्यू दिल्ली और एमपी काउंसिल ऑफ साइंस एंड टेक्नोलॉजी भोपाल के संयुक्त तत्वाधान में आयोजित कर रहा है। तो आप सभी दर्शकों से मैं अनुरोध करूंगा कि हमारे साथ इस प्लेटफॉर्म पर जुड़े रहें, क्योंकि जस्ट ही कुछ ही क्षण में हम आपके सामने लेकर के प्रस्तुत होंगे एक छोटी सी डेमोन्स्ट्रेशन अबाउट द नेशनल साइंस डे एंड द एग्जैक्ट इफेक्ट जो हम, जिसके लिए हम मनाते हैं राष्ट्रीय विज्ञान दिवस, जिसको रमन इफेक्ट के नाम से हम सब लोग जानते हैं, उस पर एक छोटा सा प्रेजेंटेशन, उसके बाद लाइव डेमोन्स्ट्रेशन ऑन स्कैटरिंग ऑफ लाइट। सो विदाउट टेकिंग मच ऑफ योर टाइम, आई वुड रिक्वेस्ट माय colleague to please open the presentation.
जब शुरू करना है बोलिए, बोलेंगे, स्टार्ट करेंगे। Good afternoon to you all. Welcome you to this program, demonstration program on the scattering of light that we are organizing in the context of the celebration of National Science Day on 28th of February 2021. As you know, National Science Day is celebrated in honor of our Indian Nobel laureate physicist Sir C.V. Raman, who happens to have discovered the landmark Raman effect in the year 1928, which is basically a new kind of scattering. So in today's program presentation, we'll be showing you some basic experiment connected with the scattering of light, and through our demonstration presentation today, we will try to explain the natural phenomena. First of all, why is sky blue? Why is she blue? Why the setting sun and rising sun look red? And how the scattering phenomena of light is responsible for this natural phenomena we'll be highlighting through our demonstration today. But before that, I'd like to share with you some basic concepts regarding the scattering of light through a brief PowerPoint presentation. As I've told you, National Science Day is celebrated in honor of our Indian Nobel laureate physicist Sir C.V. Raman, who did pioneering research in the field of scattering of light. Sir C.V. Raman, on his return trip from London to Bombay, aboard the steamship SS Narkunda in 1921, as the ship was passing through the Mediterranean Sea, Raman was intrigued by the blue color of the sea. So he wondered why the blue color of the sea is reduced. Before him, Lord Rayleigh, the British physicist, explained that the blue color of the sea is merely due to the reflection of the blue sky. But Raman did not accept Lord Rayleigh's reasoning that the blue color of the sea is because of the reflection of the blue sky. He did certain experiments on the deck of the ship. We are in equal prism with him. He had some pocket spectrometer with him. So with all his gadgets, he did a series of experiments in the deck itself of the ship. And he came to a conclusion that certainly the reflection of the sky in producing the blue color is not responsible. On reaching Bombay from the trip, he kept himself busy in a series of experiments, exploring and investigating about the blue color of the sea. He came to a conclusion on the basis of the experiments that the blue color of the sea is nothing but due to the scattering phenomena of light by the water molecules of the sea. So, before we move on to our demonstration, to explain why the blue color of the sea is there, why the blue color of the sky is produced, why the setting sun and the rising sun looks red, before we go on to actually demonstrate to our experimental setup these principles, this phenomena, I would like to share with you some basic concepts regarding the scattering of light. What scattering is all about? Scattering of light is the phenomenon in which light rays get deviated from its straight path and striking an obstacle like dust and gas molecules, water vapors, etc. As you know, light consists of a stream of photons. The photons carry energy. As the photons move on and collides with matter, atoms, and molecules, then there is an interaction energy between the photons and the molecules or atoms of the matter. Molecules or atoms, the electron, the nuclei of the molecules or atoms are embedded in an electron cell of electron cloud. So as the photon interacts with matter, with the atoms and molecules, the electrons start vibrating. And as the electrons start vibrating, they re-emit certain radiations. And they re-emit this in all directions. So this re-emission of electron, re-emission of electromagnetic radiations, all the directions is called the scattering. It's somewhat different than reflection phenomena. In the reflection, radiation is emitted only in a specific direction. But in scattering, the radiation is emitted in all possible directions. The scattering is the deep direction of electromagnetic energy by suspended particles in the atmosphere. As you know, atmosphere contains many suspended particles, like dust particles, we have smoke particles, we have water vapor. So and they re-emit radiations in all possible directions. That's what scattering is all about. But the nature and the degree of scattering depends on the size of the particles scattering electromagnetic radiations and also on the wavelength of the incident light. It is very important to note that the degree and nature of scattering depends on the size of the particles and the wavelength of the incident energy. If we have the size of the particles is less than the wavelength of the incident beam, then we have scattering popularly called the Rayleigh scattering. If we have the size of the particles approximately comparable with the wavelength of the incident beam, we have a kind of scattering called the mean scattering, MIE. If we have the size of the particles more than the wavelength of the incident beam, we have a scattering called selective scattering. So it is very important to note that the kind of nature and the scattering depends on the size of the particles and on the wavelength of the incident energy. I think here the basic definitions of scattering and on what factors does scattering depend, then we'll be telling you some of the phenomena that we experience in our day-to-day life, scattering phenomena in nature. In fact, the blue color of the sky is due to the scattering of light waves by the dust particles in the atmosphere. Had there been no dust particles in the atmosphere, had there been no atmosphere at all on Earth, the sky wouldn't have looked blue. The blue color of the sky is simply due to the scattering phenomenon of light waves by the dust particles in the atmosphere. Similarly, the setting sun and the rising sun looks red, again because of the scattering of light. The clouds look white because of the scattering of the light waves by the water drops of the clouds. The sea looks blue because of the scattering of light waves by the water molecules of seawater. So these are some of the examples where we find the manifestation of the principle of scattering of light in nature. Now, There are two different, there are two different kinds of scattering of light. First one is the elastic scattering, and number two is the non-elastic scattering. Elastic scattering, example of elastic scattering is telling you details about Rayleigh scattering, the subsequent portion of my presentation. And an example of non-elastic scattering is the Raman scattering. First of all, we'll be discussing about the elastic scattering of light. In an elastic scattering, between a photon and the scattering particle, total energy is conserved. That means the energy carried by the photons as they interact with atoms and molecules of matter, they transfer some of their energies to the atoms and molecules of the matter. So the electrons, they start vibrating and oscillating. So as the electrons start vibrating and oscillating, they re-emit again the electromagnetic radiation with a certain frequency, with a certain energy and certain wavelength. So the energy of the electromagnetic radiations emitted by these electrons must be equal to the energy of the incident photons in an elastic kind of scattering. That's why the total energy is conserved in an elastic scattering. Number 2 point says that implies that the internal energy of the scattering particles is not changed. The atoms with which the photons interact, the atoms, as the photons transfer some of their energy to the atoms of the molecule, to the electrons of the atoms and the molecules, the atoms, if they are promoted to the next excited state, next virtual state, they must return back to the ground state again. Their internal energy is not changed. That is, there is no electronic excitation or de-excitation involved. In an elastic scattering, electrons are not excited or not de-excited to their virtual states. The electrons simply remain in their ground state. Number 3 point, in an elastic scattering, the wavelength of the scattered light is not changed. It's very important to note that in an elastic scattering, the wavelength and the frequency, because the energy of the scattered light is not changed, so there is no change in the wavelength or the frequency of the scattered light. One of the examples of elastic scattering is Rayleigh scattering. It's named as Rayleigh scattering in honor of the famous British physicist Rayleigh, who discovered this phenomenon in 1871. What is Rayleigh scattering is all about? It is the predominantly the scattering of light by particles much smaller than the wavelength of the radiation. As I have told you, the degree and the nature of scattering depends very much on the size of the suspended particles, depends very much on the size of the particles of the medium. So if the size of the particles is less than the wavelength of incident radiation, then we have a kind of scattering called the Rayleigh scattering. In Rayleigh scattering, radius of the particles is less than approximately 1/10 the wavelength of the radiation. So if we have a radiation in the visual range, the electromagnetic radiation in the visual range, so we have all the wavelength extending from 400 nanometer to 700 nanometers. That means for Rayleigh scattering to occur, the radius of the particles should be less than 1/10 of the wavelength of the radiation. That means the radius of the particles should be less than 40 nanometer to 70 nanometer, 1/10 of the wavelength of the radiation. The process has been named in honor of Lord Rayleigh, who in the year 1871 published a paper describing this phenomenon. In Rayleigh scattering, the shorter wavelength blue color is scattered most, and the longer wavelength red color is scattered least. It is very important to understand that although in Rayleigh scattering, there is no change in the energy of the scattered radiation because it is an elastic kind of scattering. Although there is no change in the energy of the radiation, but there are some wavelengths which are scattered more, and there are some wavelengths which are scattered less. In fact, there is a formula. The intensity of the scattered light is inversely proportional to the fourth power of the wavelength. I repeat again, the intensity of the scattered radiation is inversely proportional to the fourth power of the wavelength. That means the shorter blue wavelengths of the visual range will be scattered more. Blue light will be scattered more, and a longer red wavelength will be scattered least. So in Rayleigh scattering, because it is an elastic kind of scattering, although there is no change in the energy of the scattered radiation, but there are some wavelengths which are scattered more, and there are some other wavelengths which are scattered least. In the visual spectrum, we have the longer wavelength red scattered least, they are scattered to the minimum extent. And in the visual spectrum, visual range of the electromagnetic spectrum, we have the shorter blue wavelength which are scattered more. They are scattered to the maximum extent. Blue is scattered to the maximum extent, and red is scattered to the minimum extent. So that is the hallmark of Rayleigh scattering. We'll move on. Now, having clarified all these concepts regarding the scattering of light, elastic scattering of light, now we are in a position to explain the blue color of the sky. The blue color of the sky is an atmospheric effect. Our atmosphere contains many particles that scatter light. The atmosphere contains dust particles. The atmosphere contains smoke particles. It is water vapor. So there are some particles in the atmosphere whose size is less than the wavelength of the sunlight, wavelength of the incident beam. So these particles will scatter light rays in accordance with Rayleigh's law of elastic scattering. Gases and particles in the atmosphere, Earth's atmosphere, scatter sunlight in all directions. But which light is scattered more? The shorter wavelength blue light is scattered more than the other colors. So as light rays from the sun is coming and entering into our atmosphere, please have a look at this slide. That sunlight is sunlight that comprises of all different wavelengths, all different colors, starting from violet to red, extending the blend extending from 400 nanometer to 700 nanometer. So as the visual part of the spectrum, the visual white light travels through our atmosphere, and they suffer scattering as they encounter dust particles in the atmosphere. So as the white light, sunlight is scattered in the atmosphere, blue light is scattered more. Blue light is scattered most. So blue light is spread out in all directions. If sun is at one part of the sky, if you are looking at the other part of the sky opposite to the sun, then it is the predominantly blue light that reaches our eye, because blue light is scattered more and is spread out in all directions. It may happen that the violet light, because of the shortest wavelength, violet light has an even shorter wavelength than blue light. So violet light will be scattered most. So we should see the sky as violet, but our eyes are not very sensitive to violet part of the spectrum. Our eyes are more sensitive to the blue part of the spectrum. So blue light is scattered more by the atmospheric particles as sunlight enters into the atmosphere. So blue light is spread out, and it is predominantly this blue light that reaches our eye, and we see the color of the sky as blue. Now, having explained why the color of the sky is blue, now we'll be in a position to explain why does the sea looks blue. The sea looks blue not because of the reflection of the sky. As I've told you, Lord Rayleigh explained that the blue color of the sky is simply due to the reflection of the blue color of the sea is simply due to the reflection of the blue sky. But Raman didn't accept this reasoning, this explanation, and he, with the help of a series of experiments at home, he proved conclusively that it is due to scattering of light. The reason the ocean is blue is due to the absorption and scattering of light. The water particles absorb the energy of the sunlight. As water particles absorb this energy, the electrons in the atoms and molecules of water particles, they are set into motion. They keep on vibrating. As they keep on vibrating, they re-emit the radiation. Okay, but the radiations in the blue wavelength, they are scattered more. Because they are scattered more, they are spread out in all directions. Because they are spread out in all directions, it is predominantly the blue color that reaches our eye from the sea water. It is similar, something similar to the scattering of blue light in the sky. So the blue color of the sea water is nothing but due to the scattering of light rays by the water particles of the sea. Now, having explained why the sky is blue and why the sea is blue, will be in the position to explain why the rising of the setting sun look red. Again, that is due to the scattering phenomenon of light. During sunset, sunrise and sunset, the rays have to travel a longer part of the atmosphere. Please look at this slide. We have the Earth here. Earth is surrounded by an envelope of atmosphere. During sunrise or sunset, when the sun is nearer to the horizon, the sunlight traverses the longest path inside the atmosphere compared to the situation when the sun is overhead at the noon time. That time sun rays travels the shortest path in the atmosphere. But because during sunset and at sunrise, the sun is nearer to the horizon, so sunlight traverses a longer part in the atmosphere. So there is more of scattering during sunset and sunrise time. So as light rays from the sun is entering into the atmosphere, the light rays get scattered by the dust particles and many other kinds of particles in the atmosphere. The blue light will be scattered most. As blue light is scattered most by the particles, so gradually, increasingly the blue light is eliminated out of the incident sunlight. So as blue light is increasingly eliminated from the sunlight, as the sunlight penetrates more deep and deep into the atmosphere, blue light is eliminated. So the white incident light minus the blue light, what color is it? It is a red light. Okay, so the red light is able to penetrate the atmosphere and reach the observer's eye. Because blue light has been eliminated. Blue light, after wavelength, blue light is suffers more of scattering. It is eliminated eventually. Only the red light, longer wavelength red light is able to reach the observer's eye. That's why the setting sun and rising sun looks red. So, through our presentation today, we have described the elastic scattering, and on the basis of the elastic scattering, we have tried to explain why does the sky look blue, why does the sea look blue, and why does the rising sun and the setting sun look blue. There is yet another kind of scattering that is called inelastic kind of scattering. In an inelastic scattering between a photon and the scattering particle, total energy is not conserved. So whatever energy is carried by the photons as they interact with matter, atoms and molecules of the matter, electrons in the atoms and molecules of matter, they are promoted to the next excited state. They are promoted to the virtual states. Okay. When they'll come back, they will not come back to the ground state. They'll come back to another excitational state. In that case, the electrons may emit a kind of radiation which energy is different than the energy of the incident photons. In that case, the internal energy of the scattering particles is changed. So as the internal energy of the scattering particles are changed, we have a radiation which energy, which frequency, which wavelength is different than the radiation of incident light. The scattered radiation is having different wavelength, different frequency than the incident light. But that's inelastic kind of scattering. But in an elastic kind of scattering, the scattered radiation must have the same wavelength, same energy, and same frequency as that of the incident light. But in an inelastic kind of scattering, the wavelength of the scattering light is changed. Raman scattering is a kind of inelastic kind of scattering. We'll be not dwelling much upon the Raman scattering or inelastic scattering. We'll move on. Raman scattering is a prime example of inelastic kind of scattering. What Raman scattering is all about is an entirely new kind of scattering. When a beam of monochromatic coherent light, like a laser beam, travels a dust-free transparent sample of a chemical compound. In fact, Raman discovered his Raman effect with alcohol as the sample of the scattering medium. So as a beam of monochromatic coherent light passes through a transparent medium, most of the light is transmitted, passes through the medium, but there is a very small fraction of the light emerges in directions other than that of the incident beam. In that case, the photon interacts with the molecules of the medium and changes the molecules' vibrational, rotational, or electronic energy. In that case, we have a scatter radiation whose wavelength, whose frequency, and whose energy is different than the incident radiation. Raman scattering is relatively a weak phenomenon. The number of photons scattered is very small. Hardly 1 in 10 million photons undergoes Raman scattering. So it is very weak phenomena. That's why it explains why Raman scattering has not been discovered for so long a time until it has been discovered by C.V. Raman in the year 1928. Unlike Raman scattering, Rayleigh scattering is a strong kind of scattering, a strong phenomena. Raman scattering is a weak process. It's very difficult to observe Raman scattering. But I like to say that it is the ingenuity of Raman who discovered a very weak scattering like Raman scattering with the help of an apparatus spectrometer at just 500 rupees worth at that time in Indian Association of Cultivation of Science, Kolkata. Now we'll go to the demonstration. The materials that will be required for our demonstration today to explain why the blue color of the sky is there, explain why the sea is colored blue, and why the rising sun and setting sun looks red. We will be setting up the apparatus right now. So what are the materials required to set up the apparatus? The materials required today, but setting up the demonstration on the scattering experiment is a white light source. We should have a white light source which contains all the wavelengths of the visual spectrum starting from 400 nanometer to 700 nanometer. We should have a round bottom flash of 500 ml capacity. Then we should have some chemicals. By chemical reactions, we'll be producing the scattering particles in the medium. Precipitation reaction occur as scattering particles whose size is much smaller than the wavelength of incident beam will be produced in our medium. So we will carry out chemical reactions with sodium thiosulfate powder 10 gram and concentrated sulfuric acid 5 ml volume. We will be taking that and we will be taking a white screen to project the scattered beam on the white screen. So these are the materials today that we will be using to carry out our demonstration on the scattering phenomenon of light. Mind you, this is elastic scattering of light. We'll be talking about, we'll be carrying out demonstration based upon this elastic scattering of light. Okay. And the schematic diagram of the demonstration is given there on your slide. We have S, the source of light, source of white light. The white light will radiate wavelengths of all wavelengths in the visual part of the spectrum, starting from 400 nanometer to 700 nanometer. The source of white light is placed at the focus of the convex lens L1. So as rays from the white light source diverges and passes through the convex lens, it gets parallel. The parallel beam of light is allowed to pass through the scattering medium. The scattering medium, basically liquid, is taken inside a container. So we have some chemicals there, and by the reaction of the chemicals to producing the scattering particles, basically we will be producing a colloidal solution with sulfur as the scattering particles, microscopic sulfur as the scattering particles. So as the white light beam will pass through the scattered medium, blue light is expected to be suffering more of scattering. So blue light, the container should turn blue, and blue light will be increasingly eliminated out. Now here we have a cardboard having a circular slit here. The circular slit will block some of the marginal rays. It will allow only the rays which are closer to the focus of the lens, to the center of the lens to pass through. And the rays will pass through a second lens L2. The second lens L2 will focus the scattered beam onto a screen. This is a screen. On the screen, we'll be able to see the remaining light of the white light after the blue light has been eliminated and scattered away. So this is the chemical sunset experiment that we'll be carrying out subtly. And thank you all for going through my presentation. Now we'll be switching over to the demonstration.
Okay. Okay, thank you, Saul sir. So this was the entire presentation about our today's demonstration on scattering of light. Likewise, previous years, this year's National Science Day also has a special theme, that is Future of STI, Science, Technology and Innovation, Impacts on Education, Skills and Work. So इस थीम पर इस वर्ष का राष्ट्रीय विज्ञान दिवस, नेशनल साइंस डे हम मना रहे हैं। तो अब आपका ज़्यादा समय ना लेते हुए हम ले चलेंगे आपको इस एक्सपेरिमेंटल सेटअप की तरफ, जिससे हम आज के इस एक्सपेरिमेंट, इस डेमोन्स्ट्रेशन को परफॉर्म करने जा रहे हैं, जिसका नाम है ऑनलाइन स्कैटरिंग ऑफ लाइट। ये आपके सामने दो स्क्रीन दिखाई दे रही होगी। ये आपके सामने दो स्क्रीन दिखाई दे रही होगी। एक तरफ हमने अपने एक्सपेरिमेंटल सेटअप को रखा है और दूसरी तरफ जो स्क्रीन आपको दिखाई दे रही है उस पर आप जो स्कैटरिंग इफेक्ट आएगा उस स्कैटरिंग इफेक्ट को देख पाएंगे। आवश्यकता पड़ने पर हम और भी क्लोज व्यू के लिए और भी एडिशनल कैमरा का यूज कर सकते हैं। बाय द टाइम, बी विथ अस एंड एंजॉय द एक्सपेरिमेंट।
Welcome you back, dear viewers, to our demonstration session on the scattering of light. We have set up our apparatus here. You might have a good look at our apparatus. We have a small optical bench here. We have used a torch lamp as a white light source that contains all the wavelengths in the visible part of the spectrum. And we have taken our scattering medium inside a round bottom flask. We have taken water out there. We'll be mixing two chemical reagents there. One is the sodium thiosulfate solution. Another is the concentrated sulfuric acid. So as the two reagents will mix, some products form, we'll have finally sulfur powder will be formed and precipitated. This will fill the entire round bottom flask. So these finally sulfur particles will be scattering our white light beam. And to project the scattered light, we'll have a screen out here. The idea behind taking the scattering particles inside a round bottom flask is that the round bottom flask, apart from containing the scattered medium, will act like a lens. So it is doing away the job of using lenses. There's no need of using additional lenses. Just the round bottom flask will itself act as a lens. It will focus the scattered beam right onto our screen. So this is the basic setup. We have the optical bench out here. We have the incident beam. We have the scattered particles that will be produced inside this round bottom flask, and the scattered beam will be focused onto the screen. The screen is basically a translucent paper, butter paper, so that we'll be able to see the scattered beam applied. We'll be able to see the effect from both sides of the translucent screen. You can either see it from the front side, from the torch side, or you can see behind the screen. That's why we have put a translucent paper to serve as our screen. So here we go. We'll begin this experiment. So first of all, we'll light up on the torch lamp. Please light up on the torch lamp, switch it on. As the torch lamp is switched on, now we'll produce the scattering particles. We have taken some water inside the round bottom flask. We'll be put some sodium thiosulfate crystals there. We'll put some 1.5 spoonfuls of sodium thiosulfate crystals there. Yes. Now using a glass rod, we'll be stirring it well, so that sodium thiosulfate crystals will thoroughly mix with water. It will thoroughly dissolve in water and go into solution. We'll be stirring it well, so that all the sodium thiosulfate crystals goes into solution. Sodium thiosulfate is a white color crystal. Yes. So we have the solution of sodium thiosulfate in water. Now we will be taking concentrated sulfuric acid. This is concentrated sulfuric acid. Because it is concentrated sulfuric acid, it is highly corrosive, so should be a bit careful while handling concentrated sulfuric acid. We are taking it with the help of a glass rod. We should avoid the contact of this acid with our skin by taking it in the glass rod, in a glass tube, and we are pouring concentrated sulfuric acid inside the flask that contains sodium thiosulfate solution. So both the reagents will mix and they'll chemically react. As the chemical react, sulfur particles, microscopic sulfur particles will be precipitated. As sulfur particles will be precipitated, this will scatter the white light. As you know, blue light is scattered more. Gradually, sulfur particles are being produced inside the flask. The flask is increasingly turning blue. It will take some time for the complete reaction to occur. The flask is turning blue because blue light is scattered most by the precipitated sulfur particles. Now, please look at the spot on the screen. It is increasingly turning red. So as blue light is scattered more and more, it is being eliminated from the original white light incident beam. As blue light is eliminated more and more from the original white incident beam, so white light minus the blue light is predominantly yellow. So the screen, the spot on the screen, is turning predominantly red. As the blue light is eliminated, we have predominantly red light. The screen is increasingly turning red, and the flask is increasingly turning blue. So that demonstrates the scattering effect of light. It is elastic scattering of light. The shorter blue wavelengths are scattered most, and the longer red wavelengths are scattered least. This is the sunset experiment. With the help of this experiment, you can demonstrate the natural phenomena that sun looks red, crimson red during sunrise or sunset. So as you look to the screen, you can find the spot becoming increasingly reddish because the blue light has been eliminated away by the scattering effect of the particles of the medium. It is the sulfur particles which are scattering the light. The sulfur particles are reduced inside this round bottom class as the product of the chemical reaction between the two reagents. The sulfur particles are just scatter the blue light away. As blue light is increasingly removed out of the white light source, we are getting the red light which is being focused onto the screen. This is the reason why sun looks red during sunset and sunrise. This is the reason why the sky looks blue. This is the reason why the sea water looks blue. So with the help of this experiment, we'll be able to explain how the scattering phenomenon of light is responsible to explain the blue color of the sky and the blue color of the sea and the red color of the setting and rising sun. It will take some time for the reaction to get complete. The white light beam, as it traverses through the scattering medium, is the colloidal microscopic sulfur particles that we have in the round bottom class to serve as the scattering medium. In the white light that passes through the scattering medium, it suffers scattering. And as you know, the blue light, because of the shortest wavelength, is scattered more. The blue light is scattered more and is spread out in all directions. It is the predominantly blue light that reaches our eye, and you see the color of the flask as blue. As blue light is increasingly eliminated and removed from the white light beam, what is the resultant light? The resultant light is red. We have the red light focused on the translucent screen. So we have the color of the liquid inside the container turns blue, while the spot which is being focused on the screen turns red. So this experiment, this chemical experiment helps to understand better the natural phenomena where the sky is red, sky is blue, and where the setting sun or rising sun looks red. The chemical experiment that we have performed, but we should be very careful while carrying out this chemical reaction, because the two reagents that we have used, one of the reagent is concentrated sulfuric acid, which is a highly corrosive acid. We should keep our body parts away from the acid, and we should not inhale the white fumes coming out of the acid, which is highly risky for our health. We should keep our body parts away from the contact of the acid. And while performing this chemical experiment, we should stay protected by wearing on the gloves so that the acid doesn't come in contact with our hands. We should use specs so that the acid doesn't come with our eyes. And we should also cover our nose with a mask so that we should not inhale the quite strong fumes of the sulfuric acid. So we should be very careful carrying out this chemical experiment, especially the strong sulfuric acid. We should be very much aware of by staying ourselves protected and following certain precautionary measures. And after carrying out this chemical experiment, we should wash our hands thoroughly under the tap with water. This is a bit of cushion that should sound while carrying out its experiment with these chemical reagents. And once you do that, the product being formed is sulfur particles, being formed, microscopic sulfur particles being formed inside the ground flask, and the sulfur particles, they fill up the medium, they scatter the white light, predominantly blue light is scattered more, and as blue light is eliminated, so we have the resultant red light that is focused onto the screen. So you have two colors visual here. One is the blue color of the container, and another is the red color of the spot. Again, it is due to the scattering phenomenon of light. Thank you.
इसीलिए क्या करोगे?
sorry, maybe my voice was not coming at that time. So I just want to say thanks to all our viewers of the program, जिन्होंने भी हमारे साथ ऑनलाइन रह करके इस कार्यक्रम को देखा, इस ऑनलाइन डेमोन्स्ट्रेशन ऑन स्कैटरिंग ऑफ लाइट को देखा। और इसी क्रम में आगे बढ़ते हुए और इस कार्यक्रम को समापन की ओर ले जाते वक्त मैं यही कहना चाहूँगा कि जो भी कार्यक्रम इस दौरान ऑर्गेनाइज किए जाएंगे 22 फरवरी से 28 फरवरी के दौरान, या जो ऑर्गेनाइज किए गए हैं, जैसे कि ड्राइंग कॉन्टेस्ट, ऑनलाइन क्विज कॉन्टेस्ट और जो कि टीचिंग एंड डेमोन्स्ट्रेशन कॉन्टेस्ट जो कि कल होने वाला है, इन सभी के रिजल्ट्स को हम अपने सोशल मीडिया पेजेस के माध्यम से डिक्लेयर करेंगे। तो आप सभी लोग हमारे सभी सोशल मीडिया हैंडल्स पर बने रहें, हमारे फेसबुक पेज को लाइक करें और यूट्यूब चैनल को सब्सक्राइब करें और हमारे साथ बने रहें, और इस तरह के सभी, ताकि आप इस तरह के सभी प्रोग्राम्स की जानकारी पूर्व में प्रायरली आपको मिल जाए। सो वंस अगेन थैंक्स टू ऑल ऑफ आवर व्यूअर्स ऑफ द प्रोग्राम एंड अ वेरी हैप्पी नेशनल साइंस डे to all of you from the entire team of Regional Science Center, Bhopal. Thank you very much.